So we have made a really great effort at deriving analytical models for how current in a short channel transistor differs from that in a long channel transistor. But at the end of the day, modern transistors are way too complicated to develop analytical models for. If you have a transistor that looks like a FinFET, for example, it really doesn't help to try to derive the current from first principles. What is more practical is that you have a set of measurements and then you try to fit these measurements into a model that describes how current relates to terminal voltages. But you have to have something to try to fit to in the first place. And so the prototypical model to which we try to fit MOSFET current is RDS equals beta into VGS minus V threshold minus zeta to the power of alpha. Now, the voltage VGS minus V threshold is always going to exist in a transistor model because this voltage expresses how much control the channel has over the channel, how much control the gate has over the channel. So this represents electrostatic control of the gate over the channel. The more voltage, the more charge the gate can couple into the channel. The constant beta is always going to contain some expression of C oxide because C oxide multiplied by this voltage is going to give us the charge that exists at the bottom of the MOS capacitor. And the more charge, the more current. So it makes sense for the capacitance to exist here. It's also going to contain W, most likely, because the wider the channel, the more the current. This factor zeta is going to be a voltage, and it's going to be pretty variable depending on what kind of transistor we are using. The power alpha is also going to be variable depending on the size of the transistor that we use. The power alpha is going to be between 1 and 2 in general, and so you don't expect it to be less than 1, and it cannot be more than 2. So let's take some typical examples of how these factors look like in different transistors. So for a long channel transistor, the good old kind of transistor we were used to, in saturation, beta would be equal to K over 2, which is equal to W over L times mu N times C oxide. So obviously we see C oxide and we also see W, and mu is an expression essentially of the velocity of the carriers in the channel. Now if we look at alpha, in this case it would be equal to 2, and if we look at zeta, then it's equal to 0. So this is for a long channel transistor. Now if we look at a transistor which suffers from velocity saturation, so perhaps we should have said that this is a transistor suffering from pinch-off saturation. In a transistor suffering from velocity saturation, on the other hand, the power alpha would be equal to 1 because we have a linear voltage to current relationship. And the factor zeta is equal to VDS sat over 2. And it's important always to notice that VDS sat is equal to a constant, and it's related to the saturation field. It's not actually a terminal voltage that is applied to the transistor. For the factor beta, it's equal to W times V sat times C oxide. So again, we see both W and C oxide outside the current, but we also see the saturation velocity V sat making an appearance. For a transistor suffering from velocity overshoot, we still see a power of 1, so that alpha is equal to 1. And obviously alpha is the most important parameter here because it represents how much more current is than voltage. So it represents how big of a saturation current we get. The higher the alpha, the better off we are in terms of delay, absolutely. And we will see why in a second. Zeta, on the other hand, is equal to 0, and beta is equal to 0.5 times W times C oxide times V thermal. So it's a higher beta because we are limited by thermal velocity instead of saturation velocity, which is why velocity overshoot current is higher than the current you would have expected if you had velocity saturation. So do we care that current is now linearly proportional to voltage rather than quadratically proportional to voltage? Do we care that that is a fact in short channel transistors? We absolutely do, because that means that delay is going to suffer. And we have to look at why delay suffers in short channel transistors, and we have to look at what else this affects. So delay is proportional to V over I. This is basically the resistance that is charging or discharging the capacitive node multiplied by the capacitance of the capacitive node. And so if we expand the expression of current, so it's proportional to V over current in a long channel transistor is going to be W over L times C oxide times V square, and capacitance is going to be W times L times C oxide. So this is going to cancel, the C oxide is going to cancel, and we will lose one of the V's, and we will lose the W, and therefore we'll get TPD is proportional to L square over V. Now, if we assume that L drops by a ratio of 1 over S, and V drops by a ratio of 1 over U, that means the TPD is proportional to U over S square. So this means that if you decrease the dimensions of the transistor, it will scale down, the delay will scale down, and it will scale down faster than linear, because in general, voltages scale down slower than dimensions. Now, if we repeat this discussion again for a short channel transistor, we find that delay is still V over I, but in this case, I is not W over L C oxide V square. Instead, we have W times C oxide times V sat, which is a constant, so it doesn't scale down, times some voltage, which is VGS minus V threshold, minus VDS sat over 2. And this is still going to be multiplied by WL C oxide, which is the C gate. So W is going to cancel with W, C oxide is going to cancel C oxide, V is going to cancel V, which means the TPD is proportional to L. So basically, if the channel length decreases, delay decreases proportionately, and delay is now decreasing at a rate of 1 over S. So if you compare a short channel transistor to a long channel transistor, you can tell why the short channel transistor is going to be slower. In fact, scaling down in a short channel domain is going to give you less returns than scaling down used to do in long channel transistors. But the fact that current is dependent on voltage linearly has even more impacts. We have always, when we talked about reducing power dissipation, when we talked about techniques to reduce dynamic power specifically, we made use of a specific identity, that TPD was inversely proportional to supply. This was always used when we used parallelism or pipelining or even slack management. It was always used as something we manipulated in order to reduce power dissipation. This is no longer true. Maybe dynamic power is still quadratically related to power supply, but delay is not inversely proportional with power supply. This is obvious just by looking at the expression of delay, because delay is proportional to V over I times C gate. Now, C gate is not a function of supply, so we can ignore it. So this is proportional to V over I. But I is no longer proportional to V square. The reason we had this identity in long channel transistors is because saturation current was proportional to the square of VGS minus V threshold. And so when VGS was much larger than V threshold, we could assume that TPD is inversely proportional to VDD. This is no longer true. In fact, if you expand the expression of current, it will give you something like this. So in fact, you can see that there is some dependence on power supply. Delay is somehow dependent on power supply, so that increasing power supply is going to reduce delay somehow, but we have diminishing returns. And if VDD is very large, you actually start to lose all dependence on power supply, and delay becomes independent of power supply. And that's kind of counterintuitive, but it's true. And it's a major problem with short channel transistors.